Imagine you've just deployed an application on an EC2 instance, and your customers are actively engaging with your website. Suddenly, the instance fails due to an issue with the underlying host machine in one of AWS's data centers. What do? Sure, you could deploy another instance, but your customers will still experience an outage even if it's just for a few minutes. Instead, what you should have done is deploy the application across a fleet of instances, distributed across multiple availability zones, and all backed by an Elastic Load Balancer. The load balancer ensures that traffic is only sent to instances that are healthy and responsive. If a single instance fails, the ELB automatically redirects traffic to other healthy instances, significantly reducing the chances of an outage for your users and vastly improving the customer experience. In this video, we will explore the AWS Elastic Load Balancer service, and we'll do a demonstration to show you how to set one up in your AWS account. Let's do this. Now, Elastic Load Balancers will automatically distribute incoming traffic across multiple targets, and targets are placed in something called a target group. These targets can be anything from EC2 instances, containers, IP addresses, or even Lambda functions. And you want to distribute your targets across multiple availability zones across multiple subnets as shown in the architecture diagram. When you configure your Elastic Load Balancer, you will associate it with a particular target group, and your target group will run health checks against those targets, identifying which resources are providing a healthy response. Your load balancer will then distribute traffic only to those instances or those resources that are responding in a healthy state. Now, you can deploy your load balancers either at the edge of your network, what we call the Internet Load Balancer. So this is where traffic is being distributed to resources within public subnets of your VPC, or internal load balancers that distribute traffic inside of a VPC against resources deployed in the private subnets of your VPC. This allows you to obviously separate out and isolate your front end from your back end, but also ensures that you're able to perform load balancing strategies both for your front end services and for your back end resources. If a particular resource fails to respond to your health checks, the load balancer will stop sending traffic to it and will instead continue sending traffic only to those resources that are responding in a healthy state. And then obviously when that resource becomes healthy again or is replaced by another instance, the load balancer can then start sending traffic to it again. In other words, your load balancer will ensure that your customers are only redirected to resources, be they instances, containers, Lambda functions, whatever it might be, that are in a healthy state, thereby reducing the chances of them coming across a page cannot be found or website not accessible type error message, vastly improving their customer engagement and experience. Now, this particular architecture isn't quite in accordance with best practices. Sure, you can deploy your EC2 instances and your containers in a public subnet, but you shouldn't really be doing that. In fact, when you're deploying an Elastic Load Balancer, actually what happens is AWS will deploy what are called Elastic Load Balancer nodes in a specific subnet that you define. Let's take a look at another architecture diagram. So here's another architecture diagram where we've actually pushed the front-end services into a private subnet environment. And obviously we've still got our back-end services as well that are further down deeper into the VPC in another set of private subnets. When you configure your load balancer, the load balancer will deploy nodes in a given set of subnets that you define. So in this case, we're deploying an internet load balancer that is deploying public-facing load balancer nodes in the public subnet of your VPC. These load balancer nodes are then distributing traffic to your front-end services, which are actually hosted in private subnets of your VPC. In other words, these particular resources, although they're providing front-end services, are not directly exposed out onto the internet. They do not have public IP addresses. It's just the load balancer nodes that are front-end facing, that are internet facing. This vastly improves your security posture when you think about an architecture design pattern. Let's take a look at the different types of load balancers that you can set up on AWS. Okay, so we'll start off with the classic load balancer. Now, the classic load balancer distributes incoming application traffic across multiple EC2 instances across multiple availability zones. Note that this type of load balancer will only support EC2 instances, however. Now, when the load balancer distributes the traffic, obviously you can define all of the EC2 instances that are to be supported by the load balancer. If a particular instance fails, the load balancer will stop sending traffic to that instance. And then obviously when that instance is healthy again, then the load balancer can continue sending traffic to it. Now, the classic load balancer is what we call previous generation, and AWS has deprecated its usage substantially. It's still available in the AWS Management Console, so you still use one, but you really should only be doing it for test or dev purposes. Okay, it really is something you need to move away from. It supports both layer 4 and layer 7 of the OSI model. So you could use it for both TCP and HTTPS traffic. It allows you to distribute traffic across EC2 instances across multiple availability zones. That's the whole purpose of load balancers. And you can configure listeners for a specified port and protocol to use, which basically allows you to define what particular type of traffic the load balancer is going to listen on and how it's going to forward that traffic to the specified resources that are registered to the load balancer. The load balancer will run health checks against your instances, and then you can define exactly what those parameters are for the health checks. Now, load balancers on AWS support cross-zone load balancing, which allows you to evenly distribute traffic across the available resources across those multiple availability zones. Let's take a little bit more of a deep dive look as to how cross-zone load balancing works, because I think it's really important to understand this feature. Okay, so let's talk a little bit more about cross-zone load balancing. Now, cross-zone load balancing reduces the need to maintain the equivalent number of instances in each enabled availability zone and improves your application ability to handle the loss of one or more instances. In this architecture diagram, we've got two availability zones. We've got availability zone A and availability zone B, and you can see that the distribution of instances across these availability zones are not the same. Okay, we've got 8 instances in the public subnet of availability zone A, but only 2 instances in the public subnet of availability zone B. When you deploy a load balancer that is not configured for cross-zone load balancing, what actually happens is that the distribution of traffic is uneven. This is because each availability zone will get half of the available traffic that comes in. And so we've got 50% of the traffic going in availability zone A and 50% of the traffic going into availability zone B. This means that each of the instances in availability zone A are only getting 6.25%, whereas in availability zone B, each of the 2 instances are getting 25% of that 50% traffic, and therefore handling far more load than their counterparts in availability zone A. This can often result in poor performance being experienced by users who are connecting to, in this case, availability zone B, and therefore the inability to handle the loss of one or more instances more efficiently. Now, if we enable cross-zone load balancing, what actually happens is the load balancer is fully aware of all of the healthy instances across all of the registered availability zones. And so ultimately, we have an even distribution of traffic across all of the registered instances to that load balancer. Each of the 10 instances getting 10% of the traffic in this example. Okay, so next let's talk about application load balancers. Now, application load balancers function at layer 7 of the OSI model and are ideal for distributing traffic based on your application design and its components. The load balancer will handle HTTP and HTTPS traffic, and that traffic will get distributed across through to listeners that you configure for connection requests from your clients using a protocol and port that you define. Okay, so in this case, you would configure your listeners with various rules to essentially accept traffic on port 80 or port 443 for your HTTP and HTTPS, etc. And the load balancer will then forward that on to the listener. Okay. Now, the rules that you define for a listener determine how the load balancer is going to route requests to its registered targets. Each rule consists of a priority, one or more actions, and one or more conditions. And when conditions of a particular rule is met, then the action is performed. Now, within a application load balancer configuration, you also need to obviously configure what are called target groups. And a target group will route requests to one or more registered targets. These could be EC2 instances, Lambda functions, IP addresses, or containers. Again, using the port and protocol that you specify. You can also register a target with multiple target groups, which is an interesting concept that the application load balancer offers. And you can configure health checks on a per target group basis. So each of your target groups have their own individual health checks where you specify the various health check parameters. So let's go through a list of some of those common features. As I mentioned earlier, it offers you routing on the layer 7 of the OSI model. So it's purely for application routing. It also offers you something called path-based routing, which allows you to create rules based on the URL path of your web application. Okay, so if you've got something that is www.mycompany.com/blog, that could go to a different target group versus www.mycompany.com shop, perhaps going to the e-commerce component of your application. Similarly, you can also have host-based routing. Okay, so where the host name is different. And you can have support for routing based on headers and query parameters. So by using query parameters, you're able to provide far more granular methods of routing into how traffic is routed to various targets within specific target groups. There's support for multiple applications running on a single EC2 instance using different port numbers. So port 80 versus port 8080 and so on. There's redirection support. There's the ability to register targets by IP address, which means that you can register targets that are outside of your VPC, for example, on-prem. There's support for Lambda functions as your targets. Containers, you can have authentication services incorporated so that you have authenticated users accessing your web application. You also have support for encryption in transit, where you can install SSL certificates using the AWS Certificate Manager. Okay, so we spoke about encryption at rest, which is where when data is at rest, you're encrypting the EBS volume, for instance. But encryption in transit ensures that the traffic from the client to the resource, to the target, is also encrypted. And for that, you would need to install an SSL certificate, and you can make use of the ACM service that AWS offers. There's support for sticky sessions, what we call session affinity, to ensure that a particular client is connected to one specific instance for the life of that transaction. And there's also integration with Web Application Firewall to provide support against web application exploitation. Things like preventing cross-site scripting or SQL injections are a typical example in this use case. Now, when it comes to actually routing traffic, the application load balancer offers a couple of algorithms that you can use, the default being the round robin algorithm. Okay, so the way how round robin works is that the application load balancer can use either what is called sequential distribution. So this is where the ALB will assign an incoming request to the next available target in a cyclic order. For example, if you have 3 targets A, B, and C, the first request will go to A, second to B, third to C, and then the fourth will go back to A. Or you can have equal load distribution, which is where it ensures that all targets receive approximately the same number of requests over time, making it simple and effective way to distribute traffic when all targets have similar capacity and performance characteristics. Now, the round robin method is useful in scenarios where all backend targets are similarly configured and capable of handling the same amount of traffic. So for instance, stateless web applications where each server can independently handle any request. Round robin helps to spread that load and avoid overloading a single server. Next, we have something called the least outstanding request algorithm. Now, in AWS, what this does is it routes incoming traffic to the target, so say for instance an EC2 instance or a container, with the fewest active requests at that moment. This sort of dynamic method of ensuring that the target handling the least amount of work receives the next request, helping to balance the load more efficiently and reduce response time in scenarios where different requests may take varying amounts of time to process, is what the least outstanding request actually helps you achieve. So you can use that sort of algorithm as well. The default obviously being the round robin algorithm. Okay, let's move on to the next type of load balancer. Okay, so next I want to talk to you about network load balancers. Now, network load balancers operate at layer 4 of the OSI model, what's known as the network layer, and they allow you to communicate over TCP and UDP protocols. Okay, now after the load balancer receives traffic, it selects a target from the target group for the default rule that you have specified. It will attempt to open a TCP connection to a selected target from the target group on a port specified in the listener configuration. Okay, so here again, you would need to set up your listener rules in order to define how that traffic flows. Now, as with other load balancers, you can design for high availability by placing your targets across multiple availability zones so that if there's an outage in a particular availability zone, well, at least you've got your instances or your resources in other availability zones to cater for incoming traffic. Couple of things to point out when it comes to the actual ports and protocols being used. So for TCP connection, the load balancer will select a target using something called a flow hash algorithm. This is based on the protocol, the source IP address, the source port, destination IP address, destination port, and a TCP sequence number. The TCP connection from the client will have a different source port and sequence numbers and can be routed to different targets. And each individual TCP connection is routed to a single target for the life of that connection. When you're working with UDP type traffic, well, the load balancer will select the target using another flow hash algorithm based on protocol, source IP address, source port, destination IP address, destination port. But the UDP flow has the same source and destination, so it is consistently routed to a single target throughout its lifetime. Different UDP flows have different source IP addresses and ports, and so they can be routed to different targets. Now, an interesting concept to bear in mind with network load balancer is that, like other load balancer, they deploy nodes within a given availability zone. Okay, and what happens here is that these nodes or these elastic network interfaces can be assigned a fixed static IP address. If this is a public facing service, as in the case of this diagram, then you can even attach an elastic IP address to your network interface for the load balancer. What this basically means is that your application can be configured to connect to a specific IP address, and therefore you can actually establish firewall rules for whitelisting purposes. Network load balancers are therefore particularly useful when you need to work with static IP addressing, when you need to work with the layer 4 protocols of the OSI model, when you need to handle millions of requests per second and volatile workloads. They support traffic over TCP and UDP connections. And they provide support for registering targets by IP addresses and can register external targets outside of the VPC as a result of that IP addressing capability. Now, one key point I want to highlight over here, your targets for a network load balancer can either be EC2 instances, IP addresses, or an application load balancer. So you can have an application load balancer daisy chained onto a network load balancer. And there are particular use cases for this, which we'll discuss next. Okay, so let's discuss how we can use an application load balancer as a target for a network load balancer. So you can create a target group with a single application load balancer as a target and configure your network load balancer to forward traffic to it. In this scenario, the application load balancer takes over the load balancing decisions as soon as traffic reaches it, and the configuration offers support for several use cases. So particularly, you will note, as per the diagram, you can make use of the AWS private link services for your application load balancer. So this will allow your customers to utilize private link on the network load balancer and to route traffic to a target application load balancer to utilize the layer 7 benefits that the application load balancer offers you. Another key benefit of using this sort of architecture is the ability to make use of static IP addressing. Often you might have some applications that need to connect to a specific static IP address, and that's not possible with an application load balancer. Application load balancers receive dynamic IP addressing, and therefore if you need to make use of static IP addressing as part of your application design specifications, then you would need to place a network load balancer in front of it. You can then assign a static IP address to the network load balancer or even an elastic IP address if that load balancer is public facing. This allows you to do things like IP address whitelisting on your firewall rules, pointing a DNS zone apex to an application front end by the application load balancer, utilizing application load balancer as a target for that LNB, for that network load balancer, and enabling DNS-A record types to be used to resolve your zone apex to the network load balancer's static IP address. You can also use this architecture when you have legacy clients that do not use DNS name resolution, and therefore you need hard-coded IP addressing. This sort of architecture is also very similar to building out the old classic load balancer, which would be used for things like utilizing multi-protocol connections. So for example, you have multimedia services that utilize HTTP for signaling or RTP for streaming. Okay, so hopefully that explains how an application load balancer fits into this sort of architecture. Okay, and where you would use an application load balancer in front of a network load balancer, and the application load balancer being a target for the network load balancer. I wanted to showcase a real-world use case. Let me show you an application that we have configured in one of our other training programs. Okay, welcome to the to-do list application. So this to-do list application is actually a demonstration application to simulate a real-world configuration where we wanted to showcase how you could build out a multi-tier stack, a multi-tier application using a wide range of technologies on AWS, from EC2 instances to containers to serverless architectures. The application is fairly simple. It's got a standard sign up and sign in form that actually runs on the back of an S3 bucket. Once you've signed up and signed into the application, however, it presents to the individual user their to-do list application. Now the to-do list application, again, is fairly simple. It performs standard CRUD, create, read, update, and delete operations against the backend relational database service running on MySQL. And I'll show you the architecture diagram in a second, but essentially this allows me to manage my to-do list. Let me bring up the architecture diagram for how this application was built, designed, and deployed. So it may look quite complex, but there are several components to this particular architecture where we had to make use of both an application load balancer and a network load balancer. Now, I'm not going to deep dive into the overall architecture here, but what I want to highlight to you is that the reason why we chose a network load balancer in this configuration is because we wanted the application load balancer, which was serving incoming requests from a REST API that runs on API gateway, to be internal. We did not want to expose the application load balancer on the edge network because we wanted all traffic from our end users to be able to go through our REST API, our API gateway, and then connect to a load balancer that's internal to the VPC. In other words, the load balancer should not be exposed out in the public subnets. So this load balancer had to be placed in an internal private subnet network. Now, there is a key behavior where the API gateway is not able to send traffic to an application load balancer that's in an internal network. And so for that, we needed to deploy a network load balancer. Okay, the network load balancer would be placed in front of the application load balancer and would redirect incoming traffic to it. The application load balancer will then handle all of the layer 7 routing and distribution of traffic thereon. However, here again, we did not want to expose the network load balancer on the edge network. We didn't want it to give it a public IP address. So we had to make use of something called an API VPC link, which is an endpoint, a VPC link service that you configure as part of a VPC, allowing the API gateway, which has the capabilities to communicate and send traffic over that private link into the network load balancer and then onto the application load balancer. And so in this architecture, we had to make use of the API VPC link because the REST API had to send traffic onto a network load balancer, which we wanted to internalize. The REST API cannot communicate with an internal load balancer. And so using an API VPC link, we were able to direct that traffic through the link into the network load balancer. Furthermore, the API VPC link cannot directly communicate with the application load balancer, and hence the reason for putting a network load balancer in front of it. So hopefully at this point, what you will start to appreciate is that in order to focus more on improving our security posture and wanting to internalize our load balancers, we had to make use of a network load balancer because we wanted to make use of an API VPC link that can accept traffic from our API gateway and then distribute that traffic on to an application load balancer that would then send traffic to the backend application processes that are running as part of that to-do list application. If you're interested in learning a little bit more about how to build this entire 3-tier application stack, incorporating the various AWS technologies that you see on the screen, and therefore building some real hands-on experience, feel free to get a copy of my AWS Certified Developer Associate Certification and Beyond book. It's currently available on Amazon and other good bookstores, the link of which is in the description box below. So next, I want to talk to you about gateway load balancers. Now, gateway load balancers are actually a slightly different type of a service. They basically help you deploy, scale, and manage third-party virtual appliances which you can purchase from the AWS Marketplace. So it gives you a gateway for distributing traffic across multiple virtual appliances while scaling them up or down based on demand. And this obviously decreases potential points of failure in your network and increases availability. Suppose you need to direct traffic to your web service, but you want to first inspect that traffic. You can procure a network appliance from the AWS Marketplace and then configure a load balancer to direct traffic to that network appliance. The load balancer will distribute traffic to the appliance for inspection. If the traffic is clean, it is forwarded back to the load balancer, which then sends it on to your web service in this particular architecture. The response follows the same route. So responses from the web server will go through to the load balancer. It will be redirected to the network appliance. If it's clean, it will continue on back to the load balancer and then sent back to the end user. Whilst all of this is happening, the actual web servers are unaware of the fact that the traffic has actually gone through that network appliance. The load balancer takes care of all of that interaction without affecting the end web server or the client in any way. If the traffic is not accepted, it is dropped. So essentially what happens is the client will send the traffic in, the gateway load balancer would forward the traffic onto the network appliance, and if there's some problem with that particular packet of data, it is simply dropped in this scenario. Okay, and it never gets to the web server. The end resources are unaware of the actions being performed by the appliances, and so this remains a critical component of this particular architecture. So gateway load balancers operate at layer 3, the network layer, where they perform packet inspection, IP packet inspection. It combines a transparent network gateway ensuring a single entry and exit points and load balancing of traffic to and from your virtual appliance. It also uses Geneve Protocol, which stands for Generic Network Virtualization Encapsulation Protocol, that operates on port 6081. Okay, so that pretty much covers all of the different load balancers that you have on the AWS platform. We've provided an in-depth overview of each of the 4 load balancers and some additional concepts and features in terms of high availability, best practices, and architecture design patterns. Next, I'm going to go ahead and give you a demonstration on how to set up and configure an application load balancer, which you can do in your own AWS account. Let's do that next. Okay, so now that we've covered all of the theory on Elastic Load Balancers on the AWS platform, I thought it would be a good idea to give you a demonstration to actually show you how to set up an application load balancer. Application load balancers are really common when you're trying to deploy websites and web apps on the AWS platform, and so getting some hands-on experience with setting up an application load balancer, it's going to be really beneficial to you. So we'll start off by taking a look at the architecture. Now, if you've been following along this course step by step, then you should already have a VPC created, the IaaS test VPC. If you haven't, you can use the default VPC, but I'll show you what the VPC needs to look like and then how we're going to add the various components to build out our Elastic Load Balancer service. So if you already have the VPC in place, or you need to set up a VPC, or you're going to use the default VPC, essentially what we're going to be doing is using a VPC that makes use of 2 availability zones. So availability zone A and availability zone B. Within this, we are going to set up our VPC with 2 public subnets, so public subnet A and public subnet B, one in availability zone A and one in availability zone B, respectively. So if you've already got this in place, fantastic. If you haven't, you need to make sure you either use the default VPC, as I said, or create a new VPC. You will also need to set up 2 security groups. Now, if you've been following along this course, then you should already have one security group set up called the Web Server Security Group. which allows inbound traffic on port 80 and port 22. But you will need another security group, which is going to be allocated to your load balancer. Yes, load balancers require security groups as well, because what you're doing there is you're specifying the type of traffic that's allowed to hit your load balancer, so that the load balancer can accept traffic on those ports and that particular specified protocol, and then forward it on to your targets. So if you don't have your security groups in place already, you will need two security groups: a web server security group for your web servers and an application load balancer security group, which you will set up in this lab. We will then be deploying two EC2 instances using a standard Linux 2 AMI and a script. Now, the script is available to you in our resources section of this video or in our GitHub repository. And using the AMI and the script, we will provision two web servers, Web Server 01 and Web Server 02. Now, the content on these two web servers will be ever so slightly different, so that we can show you and demonstrate how traffic is hitting both of those servers. So I'll explain that when we get into the console. And then once that's in place, we're going to then set up a target group. Now, because we're creating an application load balancer, you will need to create a target group. The target group is going to have a health monitoring system that will then monitor the EC2 instances we register against the target group. Once that's all in place, we then need to deploy the application load balancer configured to forward traffic to that target group. When you deploy an application load balancer, you do need to specify the availability zones and specifically the subnets within which you want to deploy the load balancer nodes. Once that's in place, the load balancer nodes will be provisioned, incorporating the security group to define what sort of traffic is allowed to hit those nodes, and they will then forward the traffic onto your EC2 instances using the health check monitoring system defined by the target group to ensure that the servers are healthy. If any of those servers are not healthy, the load balancer will not send traffic to it, and that's what we'll take a look at and simulate in the demonstration. Right, that's the architecture diagram. Let's get into the AWS Management Console. Okay, so here we are in my AWS Management Console. This is my development account. Now, I have a couple of VPCs in this account. There's the default VPC and there's the IIS test VPC. The IIS test VPC is very similar to the default VPC in the sense that it only has just a couple of public subnets. Okay, so we've got public subnet 1 and public subnet 2. And public subnet 1 is an availability zone US East 1A. Public subnet 2 is availability zone US East 1B. Okay, so two public facing subnets. Because we don't have any private subnets, we don't need any NAT gateways. We do have an internet gateway, obviously. So that's my internet gateway. And if we scroll further down under security groups, I've got an existing security group called the Web Server SG. Okay, so this web server security group is going to be for my instances that I deploy. And if you take a look at the inbound rules, currently it has two inbound rules, one on port 80 from the internet and the other on port 22. Okay, so we've got our VPC in place. If you don't have the IIS test VPC in place, you can use the default VPC, but otherwise you can quickly set up this VPC. If you've been following along our various videos till now, our course till now, then you should have the IIS VPC in place anyway. Okay, so next what we're going to do then is we're going to create another security group. Let's create another security group. Now this is going to be the security group for the load balancer. Okay, so I'm going to call this the ALB-SG, the load balancer, the application load balancer security group. Just give it the same name, ALB-SG. And that's going to go into the test VPC, IIS test VPC. We're going to define an inbound rule, which is going to be for the HTTP traffic from the internet. Because remember, the load balancer is edge facing, it's internet facing. Okay, and we're going to create that security group. Right, that's my security group created for the load balancer. Okay, now what I want to do is I also want to modify the web server security group, because I want to start taking you in the direction of best practices. So I'm just putting in the ALB name there just so that I can easily identify it. Okay, but if I go into the web server security group, I'm going to go into editing inbound rules, and what I want to do is actually remove this rule that accepts traffic from the entire internet on port 80. Okay, we don't want it to do that. Instead, we're going to re-add the HTTP traffic, but it's going to come from just the load balancer. Okay, so that means I'm going to mark the source as the load balancer security group. Now, the purpose of doing this is to ensure that it's only the load balancer that can forward HTTP traffic to our instances, because the instances are going to be attached to this web server security group. This means that anyone on the internet can't directly send HTTP traffic to our web server, which is actually a good best practice thing. Obviously, I've got port 22 open to the entire planet, which again is not ideal. You want to restrict this to just known specified IP ranges, perhaps your corporate IP range or your home IP address, whatever that might be. I'm going to leave this as it is just for the purposes of making things easy, but you want to take a look at your port 22 as well. In real world use cases, what I would strongly recommend is that you actually get rid of the SSH connection altogether and use AWS Systems Manager Session Manager. Now, we have another video on that in this series of our how-to guys, so feel free to check that out. Okay, so go ahead and click Save Rules. And now we've modified our web server SG so that it will accept inbound traffic on port 80 only from the load balancer. Okay, this is all in place. We can now go into the EC2 console. So let's go into the EC2 management console. And what we're going to do is we're going to spin up a couple of EC2 instances in our VPC in those two subnets. Okay, so we're going to click on Launch an Instance. And I'm going to call this one Web Server 01. Go ahead and use the Linux 2 AMI. Okay, so that's the Linux 2 AMI kernel 5.10. We'll stick with the T2 micro. For the key pair, you can actually leave it as proceed without a key pair, because when we connect to this, we are going to use the EC2 Connect service. However, if you are using PuTTY or a third-party SSH client, then you will need to configure your key pairs. Network settings, let's go ahead and change that to the IIS test VPC. We're going to place web server 01 in public subnet 1. Okay, this is kind of aligned with our diagram we saw earlier. We will need an IP address, a public IP address, and then this is where you select that web server SG. So click Select Existing Security Group. From the list below, select the web server SG. Scroll a bit further down all the way to Advanced Details, scroll all the way to the bottom, and you want to paste in the script that you are able to download from our GitHub repository or in the resources section of this video. And let me just quickly bring that up and show you what it looks like. So that is our script. So this is just a quick bash script. All this does is updates the operating system, installs the Apache service, starts and enables the Apache service, performs a few modifications on permissions, and then creates two files. It creates the index.html, okay, in the HTML directory of the server. And you want to make a few changes to this, and I'll show you that in a second. And then there's another file called the health.html file, which the load balancer is going to use in order to determine if this particular server is healthy. So we'll copy all of that. Okay, and paste that in there. Okay, so what I want you to do is basically make a slight modification to the echo statement, which is going to be the index.html page. Okay, there are two different background colors here. If for web server 1, use the first color, and also you want to just change this one, get rid of 2 and just leave 1 in there. And then obviously we're deploying this server in 1A. So I just want to show a little text that says this is web server 1 in availability zone 1A, and you want to get rid of this, change this as well. This is just a placeholder for you so that you know that you have to change this. Okay, so that's all in place, all looking good. That's the health check file that's going to get created, and we're going to go ahead and launch the instance. Okay, go back into the instances page. Our instance is getting launched. I'm going to launch the second instance. This is going to be in availability zone 1B. Okay, so this is going to be web server 02 Linux. We're going to use the Linux 2 AMI again. Okay, instance type is T2 micro. There's no need for key pairs for this lab exercise. Go down to network settings, IIS test VPC. We're placing this in public subnet 2. Okay, so we're distributing our instances across multiple subnets, across multiple availability zones. This public subnet 2 is in US East 1B. The other one, public subnet 1, was in US East 1A. We will also assign an IP address, a public IP address, and we will assign it to the web server SG. Scroll all the way to the bottom, advanced details, all the way to the bottom, paste in that script again, and this time we'll get rid of the first color. So we have a different color for this one. This is web server 2 in availability zone 1B, and you want to get rid of this, change this placeholder. Okay, so that is the way how you need to lay out your script, and then click launch instance again. So we'll wait for both of our instances to launch. Okay, it takes a couple of minutes, so I'm just going to pause the video over here, and we'll continue when they're all up and running and the status checks have passed. Okay, so we have now passed the status check, so both servers are up and running. We can now proceed with setting up our load balancer and target group. Remember, this is an application load balancer that we'll be setting up, so we first need to set up a target group. So if on the left hand side you go to target groups and create a new target group. So this target group is going to be having instances as targets. You can have IP addresses, Lambda functions, application load balancers, as we've previously discussed, but we are connecting to instances, so we will select that one. The name of the target group, just call it something like web server servers TG. Okay, target group. The port that we're going to be working on is HTTP 80. It's an IPv4 type address system, and we're going to place this in the test VPC, the IIS test VPC. Protocol is HTTP1, and this is where you define your health checks. So we're running our health checks on HTTP, and remember we had created a file called the health.html. HTML. Make sure you spell this one correctly, or else the load balancer will not be able to see the file that is really the health check file. If you expand the advanced health check settings, this allows you to define certain threshold values as to what you define as healthy and unhealthy. So here, what we're saying is that we want a couple of consecutive health checks to pass before we mark a server as healthy. And maybe here we'll do 3 unsuccessful health checks or unhealthy checks before we mark the server as unhealthy. Okay, I'm also going to reduce the interval time to 10 seconds just to speed up the process. And the success code we are looking for is 200, which is your standard success response code. Click next. And so now what you need to do is you need to register the targets to your target group. So these are the 2 servers that we have deployed. We're going to include these as pending. Okay, and then what's going to happen is these instances are now going to be registered with the target group when we click the create target group. So that's our target group created, and those are the 2 servers that are now registered to this target group. They're currently unused because we have not set up the load balancer yet. So the next step is to set up our load balancer. From the left hand menu, if you go all the way down again under load balancing, click on load balancers, click create a load balancer. This is where you have your different load balancers. We'll be creating an application load balancer. Let's give it a name. Web servers ALB for application load balancer. It's internet facing. Okay, so it's going to deploy the load balancer nodes in the public subnet. It's going to sit in front of our EC2 instances. It's IPv4. You're going to make sure you have to put it in the right VPC. And this is where you define the availability zones where your load balancer is going to deploy the load balancer nodes. Specifically, we're going to be deploying it in subnet, public subnet 1 and public subnet 2. So as per the diagram, you're deploying the load balancer nodes in the public subnets. Okay. The security group will get rid of the default one and attach the ALB SG that we created moments ago. So inbound traffic from users on the internet comes to the load balancer on port 80. The load balancer is then sending traffic to the EC2 instances, which is also accepting traffic only from the load balancer. So hopefully you're seeing how this daisy chain effect works with the security group configuration. Okay, scroll all the way further down. So listeners and routing. So we're accepting inbound traffic on port 80 and we're forwarding that to the target group, which will send the traffic to the targets. Leave all else as it is and then click create load balancer. Now the load balancer is going to take a couple of minutes to create, so it's currently in the provisioning state. I'm going to pause the video over here and then we'll come back to it once it's active. Okay, so our load balancer has been successfully set up. It is in the active state, and so what we can do now is from the left hand menu, go back to the target group, click on the web servers target group, click on targets, and we'll refresh this page as well. And what you should find is that your web servers are in a healthy state. And this means that the load balancer can see the health.html file. So if we click into there again, so you've got 2 healthy servers all up and running. Fantastic. Right. What that means is that we can go into the load balancers again, click on the load balancers, pick up the DNS name of the load balancer. So I'm just going to copy that to the clipboard and then open that up in another browser tab. And voila. There you have it. So we've connected to one of our servers that is sitting behind the load balancer. And so if I were to do a refresh or a few refreshes, there you go. I'm now connected to the other server and I am now alternating between the servers. So this is web server 2 in availability zone 1B. And let's just do that again. This is web server 1 in availability zone 1A. Okay. Fantastic. So hopefully you're beginning to see that how the load balancer is now distributing traffic between the 2 web servers. It will use a round robin fashion by default over a span of a particular period. But essentially it's designed to ensure that it evenly distributes the traffic across the 2 servers. Okay. Let's try something else very quickly. I'm going to go back into the EC2 instance and let's go into web server 1. We're going to connect into web server 1. So we're going to use the EC2 instance connect feature. Because port 22 is open on this server, we can actually connect to the server itself in the back end. Okay. So this is going to allow me to go into the Linux console, into the shell, and allow me to connect to my server. Okay, so here I am. I'm actually in the server. Let's just navigate to the HTML directory, and what we should find are the 2 files that were created by that script. So if I actually remove the health.html file, okay, okay, so now the health.html file has been deleted from this server. This is web server 1, remember. Okay, web server 01. If I were to go back to my console and click on target groups, and if I go back into the target group, okay, if we refresh this, and it might take a couple of seconds to pick up, but what you should find is that the target group is now not able to connect. There we are. It's not able to get that health check file, so it's now marked the server as unhealthy. Okay, so at this point, this is web server 1 that is in an unhealthy state. Because that particular file is no longer there, it doesn't respond to the health check request. The load balancer is going to say, right, this server is not responding to me. I'm going to mark it as unhealthy. And so if I were to go into the actual service and continue refreshing this page, and I'm doing it again and again and again, I'm not getting that orange screen anymore. Okay, so my load balancer is only going to send user traffic to servers that are in the healthy state. If I were to go back to my server and very quickly echo this is a health check file, just paste that into health.html, okay, and ls, and yes, my health check file is now, my health.html file is now back. Let's go back to the target group. And again, it may take a couple of seconds to actually pick it up that the file now exists. There it is. It's now picked up the fact that it can find the file again. So it's going to mark the service healthy. It's ran the 2 consecutive checks that we did as part of the health check. So remember, it was healthy threshold was 2 consecutive healthy successful checks. And so now I should be able to, if I refresh this page, there we are. We're back to our first server rather. And so now we can alternate between our servers. Okay. So this is how your load balancer works. Okay. Your load balancer is going to evenly distribute traffic across healthy instances. Right. There's one more thing we need to do as part of coming to an end of this demonstration. Load balancers are a chargeable service. They're not free. They don't fall under free tier. So now that we've got all of this in place and you have had the opportunity to test this out, what I'm going to do is I'm going to get rid of the load balancer. Okay. And I suggest you do the same. So let's get rid of the load balancer. And we'll confirm that. And you can get rid of the target group as well. So get rid of the target group. Okay. And then finally, let's obviously get rid of the servers as well, right? We don't need them anymore. So instance state, terminate, delete instance, terminate, delete. And those are your instance getting deleted. Right. Well, I hope you enjoyed this video and I hope you are going to try this out in your own AWS account and test it out, because this is going to give you the much needed hands-on practice that you need. Please do like, subscribe, and share this video with friends, colleagues, and anyone else interested in cloud computing and the AWS platform. I'll see you folks in the next video. Thank you.